Hi everyone, Mrs. Basega here, and today we're going to learn about acceleration. Acceleration has a symbol of a, and it's measured in meters per second squared. Sometimes you'll see a little arrow over the a. That means that it has direction. It's a vector. Because acceleration is a vector, it can be negative in the right way. Acceleration is defined as the change in velocity per unit time. Now notice that means its equation will be really similar to that of velocity itself. You should pause and write down this equation if you haven't done so already. Since velocity is a vector and acceleration is a vector, you'll sometimes see the velocity and acceleration both have little arrow symbols on them. But those arrow symbols don't mean that they point to the right. They just mean that direction matters for those quantities. Acceleration has units of meters per second squared. That's because velocity is measured in meters per second, and time itself has units of seconds. So meters per second divided by second equals meters per second squared. Now let's give you an example of what this means. Let's say an object has a +3 acceleration. It means that that object gets 3 meters per second faster for every second of time that passes. I'm going to make a quick t-chart here of time and velocity. Let's say an object starts at 10 meters per second. We call that its initial velocity. And every second it gets 3 meters per second faster. Well, a kind of obvious way to graph this data would be to start from 10, and for every 1 second of time that passes, this would go 3 meters per second faster, creating a nice straight upward line. This type of graph is called a velocity versus time graph. And it's useful because at every second of time, it tells you the velocity. Positive velocities indicate that the object is moving forward. So this object starts at 10 meters per second, gets faster every second, and is moving forward the whole time. Now let's add on to our model. Let's say I have a velocity versus time graph that has several segments to it. In this graph, we've got velocity versus time. This object starts at 4 meters per second and it travels at that velocity forward for 5 seconds. Because +4 is the velocity, it's traveling forward for that time, and it stays at 4 meters per second for that whole time. Now let's say it has positive acceleration, and for every second of time that it passes, it goes 1 meter per second faster. By the end of the 10th second, it's at 9 meters per second. Its acceleration is positive and it's moving forward. But let's say that it comes to a very quick stop. At 12 seconds, it stopped because the velocity at 12 is 0. During that 2-second interval from 10 to 12, the acceleration is negative, but I want to point out that a negative slope does not mean you're moving backward in this type of graph. You're still moving forward, but it's slowing down. Acceleration negative in this case means that the velocity is decreasing, or at least is becoming less positive. The velocity started at 9 meters per second and goes to 0 meters per second in 2 seconds of time. So here's what I want you to try for your homework. We're going to play sort of a matching game. And in this matching game, you'll be given a graph of velocity versus time. Your job is going to be to determine the initial speed of your object, the acceleration, and the braking rate, and then you're going to try and replicate it yourself. So let me show you how it's done. From the simulation, first I'm going to copy this graph. I blew up the homework picture so it's a little bit clearer to read. In this graph, my object started with an initial speed of 35 meters per second, which I'm reading off the y-axis. Then It has a negative acceleration. In the simulation, they call this your braking rate. It travels at constant velocity. And then it has positive acceleration, which they just call acceleration in the simulation. So I want to do 4 things with this. Thing number 1, identify the initial velocity. That's 35 meters per second. And I can tell because that's my y-intercept. Then I want to calculate the acceleration of both the positive and negative segments. During this segment, the velocity changes. It goes from 35 meters per second to 15 meters per second. That's me counting up the times there in 5 seconds. Subtracting that out, I see that I get negative 20 meters per second over 5 seconds, and that's negative 4 meters per second squared. I want to point out that doesn't mean it's slowing down necessarily. That negative 4 there means it has more force to the left than it does to the right. This would be simulated by the braking. You actually have to slam on the brakes in the part of the simulation to do this. Next, I want you to get the acceleration of the positive section by taking the final velocity of 37.5, subtracting the initial velocity of 15, and dividing again by 5 seconds. This acceleration is positive 4.5 meters per second squared. And if I've done these 3 things right, I can substitute this back into the simulation and check my work. This means there's more force in the positive direction than the negative. Maybe my free body diagram looks something like that. So now we get back to the simulation. I'm going to enter my positive acceleration of 4.5 that I just calculated. In the simulation, it doesn't let me put in negative for the braking rate. Keep in mind your braking rate is a negative acceleration. And now we're going to play. So I'm going to press the braking pedal. That's the pedal on the left for you non-drivers. And let it rest. Now notice that I'm coasting. If I'm not pressing the brake or the gas, my car coasts at constant velocity. This is an object in motion stays in motion until there's the external force. So now I hit the gas, hit the gas, hit the gas, hit the gas. I win. I have matched the graph. And last thing you have to do is record the distance traveled. This is 627 meters. All right, guys. Now you're going to be trying this on your own for 3 problems. Then I'll show you what to do with it next. Best of luck. Bye.